Okay, welcome to our sixth lesson, on motion, accelerated motion this time, and we're looking at things falling. And where this all starts is with a guy named Galileo, and he was around mid 1500s, something like that. And he had this thought experiment. He thought, and the picture's not quite accurate because he had this thought: if you stood at he's in Italy, Leaning Tower of Pisa, and you had two balls of different mass, and you dropped them at the same time, what would happen? And he actually added to his thought experiment if the two balls were attached by a string, because this affects the answer. And so he went through what's called a thought experiment of would do objects of different mass fall at different rates, right? And most people's instinct is that things that are heavier fall faster. And he was challenged by that. And the train of thought he had is that, well, if this ball was way heavier than this ball, and they were attached by a mass, then I guess this ball would go heavier, and it would go faster, and would pull this one down faster. Does that really make sense? And then this one would actually hold that one back. And he thought, you know what? It doesn't make any sense. Objects of the same mass must fall at the same rate. And even though that doesn't match our experience, he was proven to be true. The reason why we don't see it all the time, for example, if you drop excuse me, a piece of paper and you drop like a hammer, probably the hammer will land first. But the reason isn't because of something about gravity making it go faster. The reason is that air resistance affects the paper more. Okay, and we'll understand sort of the effect of things like air resistance more later on in the course. So he actually went as far as to doing a bunch of experiments. So he never actually did the Leaning Tower of Pisa experiment. What he did do was he set up an apparatus like this, and he rolled balls of different mass down, and he timed them. However, he would time them without a timer. That's a good question. How would Galileo time them? But he did come up with the conclusion that heavier balls did not fall faster. Okay, and this is a great little video from the moon.
Jim, we copied both solar wind and penetrometer drum in the ETB.
Not quite yet. I haven't put the solar wind in yet, but I will shortly. I want to watch this. I have a good picture there. I've got
beautiful picture, Dave.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Which proves that Mr. Galileo was correct in his findings.
Okay, so that is Commander Dave Scott. This Apollo 15. I don't think it was in 1969. I can't remember what year that they took that video. It wasn't the first lunar landing. But the point is, they show that in a vacuum, or on moon, there's no air, no atmosphere, so there's nothing to hold back the feather. So a feather and a hammer fall at exactly the same rate. On Earth, that wouldn't happen because the air resistance. And certainly we'll see lots of math that shows, I'll show you that that's true using math as well. And you can try it if you want in one of the laboratories. So further experimentation shows that on Earth, all objects fall with the same acceleration. And this is sort of taking into account the idea that if there was no air resistance. But acceleration does change depending on where you are. So if you're on Mars or on Jupiter, picture Jupiter, giant planet, you might guess that there's more gravity there. More gravity means things fall faster, okay? But everything falls at the same rate. assuming no air resistance, which, by the way, in physics class, we almost always assume no air resistance. And that rate is actually 9.8 meters per second squared. Okay, and let's talk about what that means. It means that this girl here, she has a little tennis ball or whatever in her hand. 1 second after she drops it, it's moving 10 meters per second. 2 seconds after she drops it, it's moving 20 meters per second. We're rounding to 10 instead of 9.8. Okay, but so, that should say 9.8 and 19.6, but this is just rounding. And the idea is just that every second, the speed moves up by 10 meters per second. And so the displacement, like the amount it falls, because between 0 and 10 meters per second, say the average is 5 meters per second, right? That's the average rate for that fall. The average rate for this fall is 15 meters per second, so it goes further. The average rate for this fall is 25 meters per second, so it goes further. The average rate for this fall is 35. So the distance traveled, or displacement, is greater between every second, but the amount that the speed changes is always the same, going up by 10s or 9.8s. Okay, so this is a very important number in the course. 9.8. Everything's times 9.8. So we always talk about the idea of free fall. And free fall means when an object is in the air, not in contact with anything else, and we assume no air resistance. And it can be moving up or down. So everything that we do in class, when something's in the air, not being held by anything, that's free fall. And it doesn't matter which direction it's going, okay? So a few assumptions we make about free fall that help calculations. We say that, when this isn't an assumption, this is just a fact, that if you throw something up in the air, at the very top, it's going to be 0 meters per second. So you throw it up. As soon as it leaves your hand, it's slowing down. It's slowing it down at a rate of 9.8 meters per second squared. But it leaves your hand. As soon as it leaves, it's slowing down, gets to the top, it stops, at least for like a tiny fraction of a second. Then it starts to accelerate in the downward direction, right? But when it gets to the top, the speed's 0. Some more assumptions we make. That there is no air resistance. So that's the wonderful thing about being in high school. One of the many, I guess. Another assumption we always make is if you throw something and it leaves your hand, and say you catch it again in your hand, you're going to catch it with the same speed. And what this picture is supposed to show is these little arrows are supposed to represent the acceleration. Acceleration is always the same. It's always down. Even though it's moving up here and going down here, the acceleration is 9.8 the whole time. It's 9.8 meters per second squared down here, causing it to slow down, and it's 9.8 meters per second squared here, causing it to speed up. So when something is in the air the entire time, its acceleration is 9.8, down. Another assumption we make, the speed of the object when caught is the same as the speed when thrown. Oh, I screwed that up. I forgot to mention here that if an object is thrown and caught at the same height, we assume the time to go up equals the time to go down. And here we're saying the speed. This is always one that gets kids a bit confused. I kind of remember being confused by it too. This last one, number 6. So when determining the speed of an object as it hits the ground, you never say, okay, when it hits the ground, it's going 0. Kind of after it hits the ground, it's going 0. But we never look at that. We're always thinking just before it hits the ground. Because all our equations that we use are talking about the idea of free fall. And once it hits the ground, the only force acting on it isn't gravity anymore. There's also the force of the ground hitting it, right? So if ever you're looking at or you're considering a situation, the speed as it hits the ground, sometimes the language will say as it hits the ground, or what it's always implying is just before, not after, okay? So it's like the speed, if it's landing right here, it's going to be like just there. Okay, just before it hits the ground, never after it touches the ground. Okay, so solving problems for objects in free fall. There's a few formulas, and I want to give them to you. They're just the kinematic formula I gave you before, but because acceleration is always 9.8, and that we take the assumptions into account, the formulas I want you to know, for dropped objects, so say you drop something, the speed just before it hits the ground or whatever, v2 would be the final speed, is 9.8 times the time. And this comes from the formulas. I'm not going to go through you just write these formulas down. keep it nice and clear for dropped objects and for objects thrown upwards, and keep them separated, and you'll be able to solve all the problems. If you're looking for the maximum height of an object and you throw it up in the air, then it's 4.9 times the t squared. An interesting thing to keep in mind is, what is that t though? If you're looking for the maximum height of something, it's the time as it moves up. So say you throw it in the air and you catch it 20 seconds later. Long time in the air, but say you do. That means the time it was going up is 10 seconds, so you'd put 10 in there. Okay? The time, that's the distance falling bit. The time to fall is square root of distance over 4.9, and or, depending on what information you have, it's 9.8 over the final speed. Okay? In the opposite direction, here's the formulas. They're similar. Okay? But if you're throwing something upwards, it has a set of formula equations, and if you're throwing them downward, it has a set. Okay, for your calculations. And you see I have d is maximum height in this case. So to use that in a example, so Ferd comes across a well and wants to figure out the depth. In order to do so, he drops a rock down the well and times how long it takes to hit the bottom. So he listens for the splash. If it takes 1.8 seconds, how deep is the well? Now we're sort of assuming that the sound travels at infinite speed, because there is a little bit of a time for you to hear, right? But we don't take that into account. So again, Ferd standing at the top of a well, drops a pebble, hears the splash, 1.8 seconds later, how deep is the well? So in this case, he's dropping something, right? So it's going to be this one. We know the time, we're looking for the distance. So you just use that formula. And 16 meters is a pretty good answer, I think. I'm going to check mark that. It's a pretty good answer. It's a reasonable depth, I think. It's not like 2,000 or something like that. One more example. Ferd would like to know at what speed he can throw a tennis ball straight up. So he throws a tennis ball and it leaves his hand. How fast is it going, right? When it leaves his hand. So he catches it the exact same spot he threw it 4.2 seconds later. So we want to find the maximum height, how far it went, and the speed with which it left its hand. So we'll start by looking at what's given, and what's given in the question is just, look, I wrote time is 2.1 seconds. He catches it 4.2 seconds later, but pretty much, we're only looking at one half of the journey. We're going to start by looking just how high it goes. So we're going to take that time and look at just the time to move up, and that's 2.1 seconds. Okay? We're looking for distance, and we're looking for the initial speed when it left its hand. So we're going to take all our time with these formulas here. And we're looking to begin with maximum height, so that's going to be this formula here, because we know the time, 2.1 seconds. We're going to solve for d. Okay? So he can throw it 21 meters in the air. And then the second thing we're looking for is what speed did it leave his hand. Okay? Looking back at the formulas, that would be V1. So we know it's moving up for 2.1 seconds. So 9.8 times 2.1 is the speed with which it left his hand. Okay? So it left his hand at 20.6 meters per second. Good work, Ferd. Good work, us. I think that's it for this lesson. So again, if you need to go through that again, or you can always ask me a question in class if you find that confused. This stuff's pretty hard for sure. So if you need some help, let me know. Otherwise, move on to your little quiz, your online quiz.